Welcome to Methods in Biostatistics. Today, we are diving into one of the most fundamental tools in statistical analysis, the z-test. If you have ever wondered how scientists can confidently claim that a new drug works or that a specific diet changes health outcomes, you are in the right place. We will build your understanding from the ground up, starting with simple intuition and moving all the way through real-world biological applications. Let us get started. To begin, let us imagine you are a baker who has been baking loaves of bread for years. You know exactly that your average loaf weighs 500 grams. One day, you buy a new type of yeast and bake a batch of 40 loaves. You weigh them and find the average is now 510 grams. Is this new yeast actually making your bread heavier? Or did you just happen to pick a slightly heavier batch by pure random chance? This is the exact kind of question the z-test answers in statistics. It acts as a mathematical lie detector that helps us figure out if a new result is genuinely different from what we expect, or if it is just a random fluke. Now that we understand the basic idea, let us look at the formal definition. In biostatistics, a z-test is a specific type of statistical hypothesis test used to determine whether the mean of a sample is significantly different from a known population mean. The test calculates a standardized value called a z-score. This score tells us exactly how many standard deviations our sample mean is away from the population mean. If this z-score is very large, it means our sample is so far away from the expected average that it is highly unlikely to have happened by random chance. When that happens, we reject the idea that nothing has changed, which we call the null hypothesis, and conclude there is a real difference. Building on that definition, we cannot just use the z-test whenever we feel like it. We specifically use the z-test when two strict conditions are met. First, our sample size must be large, which typically means greater than 30 subjects or items. Second, the standard deviation of the entire population must already be known to us. Why do these conditions matter? Because they ensure that the baseline we are comparing against is rock solid. If our sample is too small, or if we do not know how much the population naturally varies, the z-test cannot give us the mathematical confidence we need to make scientific claims. Before we look at the math, let us understand why this is so important in the real world. The z-test is an absolutely foundational tool in biological sciences, medicine, and public health. Imagine a pharmaceutical company testing a new blood pressure medication against a standard drug whose effects have been documented for decades. The researchers need to know if the new drug lowers blood pressure significantly more than the old one, not just by a tiny random margin. Without the z-test, scientists would just be guessing by looking at averages. This could lead to approving ineffective drugs or rejecting life-saving ones. It provides a rigorous, objective framework to separate true biological effects from everyday statistical noise. Now that we know why it is used, let us look at the mathematics. To figure out if our sample is truly different, we calculate the z-statistic. This formula compares the difference between our sample and the population, and then scales that difference based on how spread out the data naturally is. The symbol x bar represents the sample mean from our experiment. The Greek letter mu represents the known population mean. The numerator simply calculates the raw difference between our new result and the old standard. In the denominator, the Greek letter sigma is the known population standard deviation, and n is our sample size. The entire denominator is called the standard error. If the raw difference is huge, but the standard error is small, our z-score becomes very large, proving the difference is real. Let us apply this formula to a concrete example. A biologist knows the historical average lifespan of a specific breed of laboratory mice is 24 months, with a known population standard deviation of 3 months. She feeds a new vitamin-enriched diet to a large sample of 36 mice and finds they lived for an average of 25.5 months. We need to determine if this 1.5-month increase is real or a statistical fluke. First, we calculate the standard error by dividing the standard deviation, 3, by the square root of the sample size, 36. This gives us 0.5. Next, we divide the observed difference of 1.5 months by this standard error. Our final z-score is 3.0. This means our sample is a full 3 standard errors above the historical average. So we have calculated a z-score of 3.0, but what does that actually tell us? In statistics, we use standard critical values to make our decisions. For a standard 95% confidence level, any z-score greater than 1.96 is considered highly significant. Because our calculated score of 3.0 is much larger than 1.96, we can confidently conclude that the 1.5-month increase in lifespan was not a random fluke. The biologist has strong mathematical evidence that the new vitamin-enriched diet genuinely increases the lifespan of the mice. The math has separated the true biological effect from random chance. We've just seen how to compare one sample to a historical average, but sometimes we want to compare two entirely different samples to each other. For instance, comparing the health metrics of people in two different cities. Because we are comparing two distinct groups, we use what is called the two-sample z-test. The underlying logic is exactly the same as before. We want to see if the difference between the two groups is larger than what we would expect by random chance. However, because both groups have their own natural variation and their own sample sizes, the formula for the standard error must expand to account for both sets of data simultaneously. Let us look at how the math changes for two samples. To find the combined standard error, we take the standard deviation of the first group, square it to get the variance, and divide by its sample size. We do the exact same thing for the second group. Then, we add those two values together and take the square root of the whole thing. This combined standard error represents the natural, random fluctuation we would expect when comparing the averages of these two specific sample sizes. Once we have this new standard error, we simply subtract the two sample means to find the raw difference and divide by this standard error to get our final z-score. Let us put this two-sample formula into practice. A researcher wants to know if adult men in City A have different cholesterol levels than City B. For City A, he samples 50 men and finds an average of 210, with a known standard deviation of 15. For City B, he samples 60 men, finding an average of 200, with a standard deviation of 20. First, we calculate the standard error. We square 15 to get 225, divided by 50. We square 20 to get 400, divided by 60. Adding these and taking the square root gives a combined standard error of approximately 3.34. Dividing the 10-point difference in means by this standard error gives a z-score of 2.99. Since this is greater than 1.96, the higher cholesterol in City A is statistically significant. To truly understand what these z-scores mean, let us look at this visually. What you are seeing is the standard normal distribution curve. The horizontal axis represents our z-score, with 0 right in the middle. This middle blue area represents the natural, expected variation. If our z-score falls in this blue zone, we fail to reject the null hypothesis. meaning the result is likely just random chance. However, look at the red tails on the far left and far right. These are the rejection regions. For a 95% confidence level, these start at a z-score of 1.96. In our first example, our z-score was 3.0, placing it deep into the right side red tail. This visualizes exactly why we declared the result statistically significant. We have covered a lot of ground today, so let us review the key takeaways. First, the z-test is a powerful tool that helps us separate true biological discoveries from random chance. Second, remember the strict conditions. You must have a large sample size and know the population's natural variation. Third, whether you are using a one-sample or two-sample test, the z-score always measures exactly how many standard errors your sample mean is away from the expected baseline. Finally, when that z-score crosses a critical threshold, like 1.96, it gives researchers the mathematical confidence to declare their findings genuinely significant. Mastering this concept is your first major step into the world of inferential biostatistics. Great job today.